And it's my pleasure to introduce Anna Lytova from Ukraine. She is currently in Poland, and she is a professor at the University of Opole. She graduated from Kharkiv National University in Ukraine, doing PhD in mathematical physics. And then she worked at Kharkiv National University and at the Institute of Low Temperature Physics in Ukraine, and at the Institute and at the University of Alberta in Canada. And she is interested in high dimensional probability. She studies spectral properties of random matrices. And her main results concern central limit theorem for spectral statistics for some classes of random matrices. She wrote a number of joint papers with Leonid Pastur, who was a great contributor to random matrix theory. He also is Ukrainian. He worked both in Ukraine and in Paris for many years, and their papers have been published in top quality mathematical journals. And the same can be said about the recent papers of Anna Lytova, partly written in collaboration with Nicole Tomczak-Jägerman, Alexander Litvak, and Konstantin Komirov. Random matrix theory is a fast expanding research area with many interesting problems, and we think that it will be profitable for students to listen to a lecture in the subject. Okay, Anna, please, the floor is yours.
First of all, I'd like to thank very much the organizers for the invitation. So, is it okay if I will speak without microphone? Yes, it is sound good. I think so. I think if they will not hear me, people online, then they will vote, will write.
Well, maybe let me ask
Okay.
someone. Yes, someone online. Can you hear Anna?
Very hardly.
Yes, ma'am.
Yes. Okay.
Very hard.
Okay.
Very hardly only.
Okay. So it's better to take this microphone, yeah? No? Okay, go ahead. Is it better with this microphone? I have too many guys in my head.
It's still rather
Is
low.
it better
Much better, yes.
for people online? Might I don't know. Is it okay with this microphone?
Yeah, it's better now.
Okay. But this one is on. Okay. I hope this will do. And thanks the organizers once more time. So it's my pleasure always to come to Bendleva and to give a talk here. So I hope it works. And this will be an introductory, not advanced, but introductory lecture to random matrix theory. I was asked to give a lecture for students. I don't know about background, so this will be introductory lecture. But you can ask some questions, and we can discuss later some other questions. Okay, what I'm supposed to do is to introduce main definitions, discuss some main questions, to say a few words about the history of the subject, and to present one proof if I will have time. I hope I will have. So first, Definition is very simple. Random matrix is matrix which entries are random variables. So here we are dealing with joint probability distributions. And depending on structure of matrix, it can be symmetric, Hermitian, sparse matrix, and depending on distributions of your entries, you have many classes of random matrices. And we are dealing not with just one matrix. Usually we take sequences of matrices of given class when size of matrix tends to infinity. And of course, we are interested in spectra and eigenvalues and eigenvectors. No, we have some joint distribution, so they're not supposed to be independent. So in some cases, yes, in some cases, no. So many classes with different distributions and different metric structure. And it appears that what is important was the first, it is metric structure, and some results almost do not depend on distributions of entries. So we are interested in eigenvalues and eigenvectors. So this can be said that this discipline is the study of matrix theory in context in settings when matrices are specified probabilistically. And as a theory, this RMT, random matrix theory, lies mainly on intersection of probability theory, algebra, linear operator, group theory analysis, and then we use instruments from free probability theory, combinatorics, graph theory, convex geometry, topology, supersymmetry, and everything that we have in hand. So everyone can find a problem for every test here. And as I told, we are interested in eigenvalues. I use this notation lambda j for eigenvalues and eigenvectors, also singular values, singular vectors. And we are interested in various spectral statistics. So spectral statistic is any function which depends on lambda j by vj. Or symmetric. Because there are counterparts of all questions for non-symmetric case, but we restrict ourselves to symmetric case when eigenvalues live on real line, and we can sometimes it's convenient to order them. And there are two main regimes: asymptotic when size of matrix tends to infinity, and non-asymptotic. They usually go hand in hand, like central limit theorem and its non-asymptotic part, Berry-Essen theorem. So, and also we distinguish between global and local regimes. Global when we are dealing with intervals which contains almost all eigenvalues, and the local regime when we are working with chosen eigenvalues, for example, maximum or minimal eigenvalues. Okay. So basic question. One of the main subjects for any class of random matrices is a so-called counting measure of eigenvalues. The definition is very simple. For any interval, this measure just count how many eigenvalues fall in this interval, and we normalize it by n. So measure of the whole real line is 1. This is a probability measure. Also, we can write as a normalized sum of indicators that lambda j in data. And evidently that the density of this measure is just normalized sum of Dirac delta functions in lambda j's. And so we have sequence of random measures. And it appears that for many classes of properly normalized random matrices, they possess a self-averaging property. These random measures have non-random limit for many ensembles of random matrices. And the first question is to find this limit, to find the limit of the counting measure of eigenvalues. No, big limit. Please, this is, please pay attention that here we have two types of convergence. As measures, they converge weakly. As random variables, they converge with probability 1 or improbability, in type of convergence. So here just write what does it mean that they converge weakly, that for any test bounded continuous function phi, we have this convergence. This is just definition of the convergence. And let's pay attention that here we do not have integral. In fact, because of the definition of this measure, it is just normalized sum. And what we have here, sum of random variables divided by n has a non-random limit. So we have treated, consider this as an analog of law of large numbers of classical probability theory, but here lambda k are strongly are not independent, strongly not independent. Okay, so if we have this convergence to non-random limits, the next natural question is what is about fluctuations around this limit? So what about central limit theorem? And this is the second question to show or to check whether the centered sum normalized by some factor has a Gaussian limit. So this is the second question in global asymptotic regime. Next, we can ask some local questions. We can ask what is the distribution of maximal eigenvalue, minimal eigenvalue, what is the spacing distribution. So by the way, spacing distribution, we can order these eigenvalues and consider distances between neighbor eigenvalues, and we want to find this distribution of these distances. This is so-called spacing distribution. Also, there is a natural question, what is the probability that given matrices are invertible? And we can ask more we can ask for more quantitative estimate. It does not ask just, is it invertible or not invertible? We can ask what is the distance between smallest singular value and 0? What is the probability that this distance is less than something, 1 over square root of n, for example. And the last two questions are non-asymptotic. So we can ask non-asymptotic questions, and as to eigenvectors, we are interested in their delocalization properties. We say that vector completely delocalized if it has distribution, a uniform distribution of a sphere. Then we say it's delocalized, and we say that it's localized if it has some chosen directions, if it has some finite support. And it is very important questions, especially in applications in physics, whether vectors, eigenvectors localized or delocalized. So these are some of basic questions in random matrix theory. And today I want to focus on the first question, which is convergence of counting measure of eigenvalues. But before doing this, I'd like to say a few words about the history of the subject, about origins. And it is interesting that this theory appeared not as a logical continuation of probability theory, but deep in physics. And first, the deep results were obtained by physicists. And then mathematicians became more and more involved, especially when there was found the relation between eigenvalues of some Hermitian matrices and zeros of Riemann zeta function. And now it is great mathematical theory in its own rights with many applications in various different areas in physics, statistics, mathematics, and other branches. And the question is why so many applications and why random large matrices? Why they are interested in have so many applications. So why matrices is easy to understand because they are everywhere. Because many phenomena in physics are described with the help of Hamiltonians, which you can approximate by matrices. Then when you solve linear equations, again, you have matrices. Then you have big data everywhere, also the matrices and the graphs, networks, neural networks. and you have adjacency matrices of graphs and so on. So matrices really appears very often in applications, but they are deterministic. So why random and why large? And as usually randomness introduced artificially. It's always introduced artificially. It's just a general approach of statistics and statistical mechanics. If you have many subjects of the same nature, it is convenient to think that there is underlying distribution and you pick just these objects from this distribution. So it's like there is a plot or world of ideal forms, and these forms are distributions. And why large random matrices is because of effect of CLT, central limit theorem, and law of large numbers, because bigger, more random variables you have, more structure you have. And in practice, we do not know distributions, underlying distribution, but if n is big, you do not need to know this distribution, because for law of large numbers, it's enough to have one moment. For CLT, it's enough to have two moments. So we have this cumulative effect of big number of random variables. So what about first result? Usually we say that, okay, it starts, this series starts in statistics and the random matrix theory, but recently it was noticed by Percy Diaconis and Peter Forrester that the paper by Hurwitz, this paper of 1897, should be regarded as the origin of random matrix theory. And in this paper, Hurwitz introduced and developed the notion of an invariant measure for the matrix groups. So this paper can be considered as a first paper in random matrix theory. Then in 1928, John Wishart introduced another class of random matrices as an estimator of covariance matrix. So it is known that, it's quite natural that it is known that the basic problem in the multivariate statistic is by sampling from a high dimensional distribution to estimate its covariance matrix sigma. So suppose that we have n-dimensional vector X, random vector, and we want to understand correlation between its coordinates. To do this, to find how somehow covariance matrix, we take m independent copies of this vector and build first. We can build first matrix B, which columns are these vectors, and then sample covariance matrix is just Bn transposed, or it just normalized sum of rank one matrices x alpha t. They're just projectors of these chosen vectors. And it is easy to see if our distribution is centered, then this is unbiased estimator of sigma. Later, there was found, and in particular, if entries x, jk, if these vectors are taken from the Gaussian distributions, then corresponding matrix called Wishart matrix. What is interesting, later there was found the joint probability distribution function of the eigenvalues of Wishart matrix. It has this form, and what is important that it is proportional to the product lambda j minus lambda k, so which means that this density is equal to 0 when lambda j equals to lambda k, and this reflects that fact that eigenvalues of this matrix repulse each other. So they do not want to live together. And this is, and this repulsion effect is very important to the next application. Application in random, in nuclear physics. In 50s, the fact that eigenvalues of Hermitian matrices repulse each other helped Wigner to construct a statistical theory of energy levels for heavy nuclears. How it was in 50s, physicists had many spectra of heavy nuclears. They want to describe them, and here we have two examples. And in particular, you can notice that high energy levels do not cluster. And Wigner wanted to propose a model which will catch this properties that high energy levels repulse each other. And according to quantum mechanics, energy levels are eigenvalues of the corresponding Hamiltonian. And the revolutionary idea was to take as a Hamiltonian random Hermitian matrix. Okay. Now, Dyson described it as follows. We picture a complex nuclei as a black box in which a large number of particles interacting according to unknown laws, and statistical theory will not predict the detail level sequence, but it can describe a general appearance of level structure. So what about spacing distribution of energy levels? Even if you know distribution, joint distribution of eigenvalues, it is really difficult to find the spacing distribution from this formula because you need here to integral over n-1 dimensions. So, okay, if you can do this for n, you can take small n and Wigner and von Neumann, they took toy model when n is 2, and it appeared that n equals 2 can be big enough. So what they, just to understand what is going on with this repulsion, with spacing distributions, they took 2 by 2 matrix with Gaussian entries. Here x1, x2 are standard Gaussian, and x3 has variance 1/2. And it's easy to find here eigenvalues. Then spacing is λ1, which is minus λ2. It's just function of 3 random variables, and we want to find its probability distribution function. Okay, we can write it in this way. If you don't like delta function, you can write here indicator of the set where this is more than 0, and then take derivative, but it will give you the same answer. Then you change variable so that instead of square, what we have here r, this variable r. So this delta function kills you this variable r. So it's easy to calculate this integral anyway. And this is the answer. So here is a plot for this function. And Wigner surmised that the same behavior will be for spacing distribution for all heavy nuclears in average. What is important here is behavior around 0. We see that the density goes to 0 as goes to 0. No, you can calculate that the probability that spacing less than x will be x squared. So it goes to 0 as x squared. Okay, in general case, when you as a model Hamiltonian take n by n Hermitian matrix, the spacing distribution of eigenvalues was computed by Godin and Mehta in 60s. Also, I would like to make here more remarks. And first, okay, it is interesting to compare the situation with independent random variables. Lambda, J are strongly non-independent. What if you take n independent random variables? So you can pick n independent random variables from a uniform distribution on 0, 1. Then if you will calculate spacing distribution, you will have something like this. It will have maximum at 0. Why we have this picture? Because and this we will have approximately for all for any sample of n independent random variables.
I have a problem with PS here because for 2 eigenvalues, this was the difference. So what is now PS? P of S, what is now?
Okay. No, P of S, okay, how we constructed? How we constructed counting the measure of eigenvalues. We just take interval and calculate how many eigenvalues fall in this interval and by n. Here it's for eigenvalues. For spacing, we just take interval and we can for given we have spacings. There are numbers. Also, we can take interval, calculate how many spaces, how many distances fall in this interval, and we divide by n. Usually, we divide by average distance. So this is just counting measure of distances. Okay, and Okay, for fixed n, it's difficult to find it, but in Gaussian case, it was done by Godin and Metal, but we can find the limit as n tends to infinity. And it is important that here we, to get something like this, we need to normalize by n, not just distance, but by average distance. We need to divide. So it is easy to understand why sampling, why we have sample of independent random variables, why we have maximum 0, because if you have bell-shaped distribution, for example, and you have many points from this distribution, that many of them will fall around the mean. So that's why with high probability, many of them will be close. So for independent random variables, we have this curve, and for strongly non-independent, we have this so-called Wigner surmise. And one more very important remark, that later Wigner, Dyson, Godin, and Metal formulated the famous universality conjecture that this local eigenvalue statistic, like for example, the spacing distribution, depends only on the symmetry class of the random matrices, but not on the distributions. So you can calculate spacing distribution, for example, for Hermitian, symmetric matrices, or quaternionic, and you will have 3 different formulas, but they will depend only on class of symmetry, but not on distributions.
Sorry, I have a question. In the second point, these variables are uniformly distributed, yes?
Yeah.
And in more general case, one can say something, or?
In more general case, if the main feature here is that they are independent. If your distribution, underlying distribution, has mean and small variance, and you take n independent points from the same distribution, many of them will fall around the mean. So many points will have very small distances between them. Yeah, spacing.
Yes, but you
and
have
in the limit, we will have something like this. Not exactly. No, it will be Poisson distribution.
Oh, okay.
For any set of random, very independent random variables. So instead of U01, you can take any distribution effect with having 2 moments.
So the precise formula for a given n won't be the same. It won't be e to the power minus s, but in the limit you get the same distribution, yes? If n tends to infinity.
If n tends to infinity, if you take NIID random variables, it doesn't matter from which distribution, you will have approximately this.
Okay.
It always will have this form. But in the case of when they uniform distributed on 0, 1, it is more or less easy to its classical result to calculate. In general case, no, you need to work a little bit. Okay, but this will be this distribution with maximum in 0. Okay, this is a universality conjecture, and last funny remark, but this universality goes far beyond matrices, and we can show that the same spacing distribution have eigenvalues of large Hermitian random matrices, resonance of heavy nuclear, zeros of Riemann zeta functions, bus arrival times, and birds perching on electric wire, or cars standing on parking lot, not very close, not too far. So which means generally that if you have something having this spacing distribution, this means that these things are not strongly not independent. They have some strong dependence structure. Okay, so this about spacing. And eventually Wigner introduces Hermitian matrices, which is called, but here I present Wigner real symmetric matrices. 2 main features of this class are that these matrices are symmetric matrices and entries are independent up to the symmetry condition. So if you have something like this, you have Wigner matrix, and you have some additional moment conditions for different problems. You need different additional conditions. For example, to have convergence of empirical distribution function, it is enough to have two moments essentially. To have universal spacing distribution or central limit theorem, you need to have 4 moments. So there are some results, different results depends on different moment conditions. And in particular, if entries are Gaussian with variance 2 on diagonal and 1 off diagonal, then the corresponding matrix belongs to the so-called Gaussian orthogonal ensemble. It is orthogonal not because matrix is orthogonal, but because corresponding measure is invariant with respect to the orthogonal transformation. So this is Gaussian orthogonal ensemble. So, and the first important asymptotical result in random matrix theory is due to Wigner, who finds the limit of counting measure of eigenvalues for Wigner matrices. So here, recall what is this counting measure of eigenvalues. Then almost surely, these measures converges weakly to the so-called semicircle law. It's also because we have this density. If the second moments are not 1 like here, but some A2 squared, that this density will depend on the second moment of moments. Okay, and here repeat what does it mean that density converges weakly. Okay. So this quantity, this is called linear eigenvalue statistics. It can be written as a normalized sum or normalized trace of function of Mn for any test function phi. And once more, because we have this convergence, normalized sum converges to non-random limit, this can be considered as a law of large numbers. As to the proof, there are several ways to prove such results, including Moments method, Stiltius transform method, free probability methods. Also, if you have joint probability function for all eigenvalues, you from this formula you can find the limiting distribution. Okay, and Wigner proved his result using the moment method, which says that to prove the convergence, it's enough, roughly speaking, to prove convergence of moments of corresponding measures. So it is enough to take test functions with monomials. Okay. And I'd like to say about another method, which is method of Stiltius transform, which says that here it is enough to prove this not for all functions, but for one function, namely phi of lambda equals lambda minus z to minus 1. So this is Stiltius transform. And in the remaining time, I'd like to present this method and to prove that help, show how to prove that help convergence of counting measures for sample covariance matrices. So first is Stiltius transform was introduced to the random matrix theory by two mathematicians from Kharkiv, Vladimir Marchenko and Leonid Pastur in 1967, when they study convergence of counting measures of eigenvalues for sample covariance matrices. And here I just want to present the result partially. This is the first paper, first page of the paper of 1967. So first, Stiltius transform of non-negative finite measure M, you just integral over R of M de lambda divided by lambda minus Z. It is a holomorphic function in complex plane without real line with many useful, interesting properties. I will note only that there is one-to-one correspondence between Stiltius transform and the measures. And there is an inversion formula. If you have Stiltius transform, you can restore your measure. Here, delta is any interval which whose edges are not atoms of this measure M. And moreover, this one-to-one correspondence is continuous. So in our case, what does it mean? So to find the limit of measures, it is enough to find limits of STS transforms and then apply this Perron inversion formula. So in our case, if measure is a counting measure of eigenvalues, then by the definition, this is its STS transform, and by the spectral theorem, this is just normalized trace of the resolvent. So let's remember that Mn is symmetrical or Hermitian, then we have this.
Sorry, I have a question. What does it mean that we have a vague convergence measures?
Vague convergence, it is almost weak convergence, but weak convergence is on the continuous bounded functions, and vague convergence is when test functions have bounded support. So in fact, the limit may be not probability measure. You must additionally check then that your limit is probability measure.
Okay,
so
thank you.
If you have this, always have this, then you check that the limiting measure is probability measure. And you can read about STS transform in the book by Aki-Ezra-Glassman, Linear Operators, but in every textbook on random matrices by Zituni, Anderson, Gyane, or other books, you can find everything you need to know for random matrices about STS transform. Okay, thank you for your question. So we stopped on the fact that STS transform of the normalized counting measure of eigenvalues is just normalized trace of the resolvent. And this is very important because resolvent is very nice subject to do with, because here we can apply the simple instruments of linear algebra, and also this is an analytical function. So, okay, very nice object. And so to find limit of measures, it's enough to find limit of normalized traces of the resolvent and then to apply inversion formula. Let's do it for sample covariance matrices. Here, just recall the definition. X1 to Xm are independent, identically distributed ID random vectors. Then this is a corresponding sample covariance matrix. And I do not have here normalization factor. Everything we need, we put inside X alpha. And here we consider asymptotic regime when M and N are asymptotically proportional. This makes sense from the point of view of statistics. And let's know that we should consider only finite size. And this was first asymptotic result for sample covariance matrices, the result by Marchenko and Pastor. So in particular, they proved the following statement. If Mn is our sample covariance matrix, where these vectors X alpha are ID copies of X, such that it has zero mean, and covariance matrix of X is a normalized identity. So for example, vectors uniformly distributed on the unit sphere satisfy these conditions. And let's additionally components of X are ID. Then in this asymptotic regime, we have weak convergence of counting measures to the limit having this density. Okay, so A minus A plus are edges of the support of the limiting measure. And here we have different graphs for different values of C. Let's pay attention that when C is 1, then left edge is 0. Okay, we have this graph. Okay, then there are many many generalization of this result. We can put matrix inside, the deterministic matrix inside the X alpha outside. We can add some matrix deterministic. So many generalization of this result. And first of all, we do not need entries to be IID. It is enough for them to have 0 mean and variance 1. But in this case, we need to add some Lindeberg type condition on the second moment. Also, we do not need the entries of coordinates of X to be independent. And what I want to show in the remaining time is proof of this theorem in the case when without this condition. Instead of this condition that components of X are independent, we will suppose that for any deterministic matrix, the variance for any deterministic matrix N, the variance of this bilinear form tends to 0 as N tends to infinity.
Excuse me, because I think I missed something. What are exactly the matrices? I mean, they are not Gaussian now in
No,
Pasteur.
they're not Gaussian.
They are not Gaussian in Pasteur, Marchenko. So what exactly the matrices?
They're not Gaussian. There was Gaussian only when Wishart introduced them. They were Gaussian, but we do not need them to be Gaussian. So they are just sum of rank 1 matrices where X alpha are independent vectors taken from some distribution.
Okay, okay.
And
I do some distribution. Okay, you take X alpha, X transposed alpha. Okay, but you should have Wigner distribution also. So is this Wigner distribution, this thing inside? This in the middle?
No.
Because
Here,
this covers, does it cover also the case of Wigner? Is it more general than Wigner theorem?
there is connection, but now I'm not ready to describe this connection. This cannot be treated as a generalization, but okay, there is connection.
So this is not a general. So why this is?
It is positive definite, but Wigner is not. So if you
Okay, it's positive definite.
positive definite, so and Wigner is not.
Okay. Okay. Because but anyway, these things that are on the second picture, these are just
They correspond
graphs of the limit measure. Yes, this is
Graphs-
density of the limit measure.
Yes, graphs of the limit measure corresponding to different parameters C.
See,
It
okay.
depends on C. It's,
Okay.
when C is 1, you can see that when C is 1, minus is 0. So then you have something like this. They have singularity summable at 0, square root of lambda. But in other cases, you have sign support which is separated from 0, which is important in application. Your matrix is invertible.
Okay. Thank you.
And okay, thank you for the question. And okay, philosophy is as to Gaussian distribution. Usually, we start with Gaussian distribution. With distribution which is convenient to work with. Then, having this universality in mind, if you proved something for Gaussian distribution, you hope to have this for all distributions. No, up to some moments. So you have them to have some 2 moments here. It's enough to have 2 moments. For central limit theorem, for fluctuations, it's enough to have 4 moments.
Sorry, I think that I'm also lost. Could you remind me what is M here? Small m.
M is M alpha from 1.
It's
M
the
is
number
of
of the
independent
summons.
vectors.
Okay, so since this density function has lambda in the denominator, it means that if m divided by n tends to 1, exactly 1, then we have the singularity, yes?
Yeah, but it's okay.
Otherwise, we don't have it.
Yeah, otherwise we don't have singularity, yes. Exactly.
But in any case, this density, okay, only
This will be probability density in any case.
Yes, but it is somehow similar to this semicircle, but the difference in the denominator, yes, which is this lambda, yes.
Yeah. So it looks like, in this sense, yes, it looks like distribution, limiting distributions, like semicircle law. So here you have. So I don't. It looked like semicircle, yes. So, but exact connection. So I don't now formalize this exact connection yet. So we have here for some. See, we have here shifted semicircle, like here. Okay. So now I want to present the proof of this result, the main steps of the proof. Not supposing that entries of X are independent. Instead, Fall in the paper by Pajor and Pastor, we suppose that for any matrix deterministic n, for any sequence of matrices n tends to infinity, variance of bilinear form tends to 0 as n to infinity. So, and we'll prove convergence in probability. So first notations, Mn is our matrix. We use G for the resolvent because it is green function. And as N is the main subject we are interested in, it is a Steltius transform of our measure. It's normalized trace of the resolvent. And we will use upper index alpha for things which does not depend on the x alpha. So Mn alpha is Mn minus this projector on vector x alpha. So it doesn't depend on x alpha. G alpha is corresponding resolvent, and Sn alpha is the normalized trace. So we know that because this is resolvent, it is bounded. So the sequence of Sn is uniformly bounded. So there is convergent subsequences, and we need to show that any convergent subsequence has the same limit, which is what we need. Also, let's know that because Mn and M alpha differs only by matrix of rank 1, then the eigenvalues interlace. So distance between them are less than 1 over n in average. That's why Sn alpha is Sn plus something small. Okay. The first step here is to show that the variance of Sn goes to 0 with n. Then if we want to show that this Sn converges to Sn to S, to this limit, to Steltius transform of Marchenko-Pastur law in probability. So if variance is small, then to prove convergence in probability, it is enough to show to prove convergence of means. So the second step is to find the limit of the expectations of Sn. Then if we will find this S, then our density of limiting measure is given by this formula. You just can calculate it. So we need 5 simple ingredients to prove this. First is because we have this condition, our vector is isotropic, normalized isotropic. Then expectation of this form. That's the most important fact here is that G alpha and X alpha are independent. We separate them. G alpha does not depend on X alpha. That's why it is easy for us to calculate expectation with respect to X alpha. And this will give you normalized trace of G alpha, which is expectation of Sn. So due to this relation, if we have normalized trace of G alpha, it is our Sn. Second, we have this condition that variance is also small. And then again, because G alpha and X alpha are independent, this variance is small. So next, this is trivial relation, which shows that if variance of psi is small, then expectation of reciprocal is approximately reciprocal of expectations. So that's why we can write this expectation 1 over this thing is 1 over 1 plus expectation of Sn. We just apply this to first 2 steps. And then we have from linear algebra this so-called rank-rank perturbation formula. You can check this. This is from linear algebra. Then multiplying this by x alpha, we get this relation which connects G without alpha, our resolvent, with resolvent which doesn't depend on alpha. And finally, very simple, the resolvent identity. Also simple fact from linear algebra. And here I just put inside this matrix M. So now, if you summarize everything, what we have, so we'll start with expectation of Sn multiplied by Z, by Z. Then we use resolved identity. We have this relation, equality. Then since under the trace, you can permute your matrices. This trace is just a bilinear form. So this trace is just bilinear form. And we can apply this equality and to get this. So next final step, expectation of this fraction is 1 over, so what we need, 1 plus expectation of Sn. So let's pay attention that let's note that this doesn't depend on alpha, and second m, this fraction tends to c. And finally, what we have the equation for the limit of subsequence of Sn. So if this S is limit of expectation of Sn, then, so of course we work with subsequence, but we have this for every subsequence. Finally, we have this quadratic equation. We solve this quadratic equation and we choose a solution which goes to 0 and infinity, because this is trace of the resolvent. It should go to 0 and infinity. Okay, we have S, and then we just calculate our density and get the result. So that's the end of the proof. So, and last slide is just there are many books on random matrices. I put the book by Mesa first because it was first book on random matrices and more popular among physicists maybe than mathematicians, but it's excellent book. But then we have, starting from 2010, we have many other books on random matrices. So thank you for your attention.
Well, are there any questions or comments? Maybe people online? Please ask. Please just ask.
So I wanted to ask about the connection of this random matrix theory with, you mentioned quantum field theory. So in quantum field, is interested in constructing some sort of random distribution, meaning a distribution as a generalized function. But here we deal with random matrices. So could you say something more about this connection?
No, unfortunately not. I know that there is a connection, but I know about connection with quantum information theory. There are matrices which appears in quantum information theory, but quantum field theory, I just don't know exactly.
Okay.
Quantity.
Okay, and I have a question, maybe some sort of historical question. You mentioned this paper by Hurwitz, where he was able to construct, maybe we could go back to this slide. It was about constructing invariant measures, yes? For SON and for UN. So these are compact groups, yes? So this measure were a special case of the Haar measure, yes? It was before the discovery of Haar, yes? Since
I think yes.
Mm-hmm.
This was first result of integration of this particular case of Haar measure.
Okay. Okay, thank you.
Okay, maybe there are some other questions. People online, please just speak up.
You mentioned that on some slide, I can't remember where, you mentioned that some properties of random matrices depend only on the symmetry type.
Yep.
So did you only mean that it was done, for example, for Hermitian, symmetric, etc. matrices, or has it also been researched for some abstract type of symmetry?
There are also also quaternionic matrices, so some unitary groups. So, okay, generally, what is important is a symmetric class. Then, as to distributions of entries, you only need some information about some moments, but you do not need usually to know what exactly is the distribution. But it's interesting to find example when we need knowledge about the distribution. So now we will have this universality in mind and know, okay, if we have something for Gaussian case, then we have this for everything. And it is interesting to find examples when distribution matters. And for example, we found one example. Okay, for example, central limit theorem for eigenvalue statistics more depends only on 4 moments, and this is in some sense universal example. So this is an example of central limit theorem for linear eigenvalue statistics. So look at this. You have eigenvalue statistics. You center it, subtract expectation, and as a limit, you have normal distribution. And this result depends on 4 moments, and that's it. But we showed that if you will take only one, someone here, phi of lambda j, then the result will depend on the exact distribution of entries. And this was interesting because we accustomed that, okay, we have
Okay, any other questions or comments?
So related to this slide, there is a bullet in which you wrote that phi belongs to H5 2. So this is this is a Sobolev space? Or?
Sobolev space, yeah, you have 5/2 generalized derivatives. So it's integrable with, so its Fourier transform has 5 moments. No, roughly speaking, it has 3 derivatives, so finite number of derivatives. But yes, it's Sobolev space.
Okay.
No, it is convenient here to work with Fourier transforms. That's why it's formulated via Fourier transforms of test function.
I see. Thank you.
Okay, any other questions possibly? Well, if not, let me finish with my personal memories. I met Leonid Pastor once. I should say Leonid Pastor, yes? Yep. This in Ukrainian is Pastor. Okay, so I met him in France. I don't know, it was a conference or a talk, but anyway, I assisted at his talk, and everybody in France said Pastor. Yep. You know, so for me it's Leonid Pastor, and that's why I said like that. But okay, so so thank you very much for the lecture, and maybe let's thank the speaker again.
Okay, I have 2 textbooks on random matrices with me. You can borrow until tomorrow, and we can discuss them.
Okay, so now I will just.